How do you define a black hole?
Well, it's in Einstein's theory, which again is a remarkable thing. It's published in 1915, over 100 years old. But it's just a region of space from which even light can't escape.
A black hole is a region of space and time where the strength of gravity is so high that light has no path to get out of the object. All paths through space-time curve back in on itself. Normally we think of a hole as a hole in the floor, and you fall through, come out the other side. Except it's a three-dimensional hole. You can fall in any direction.
And so black holes, they're kind of a metaphor in a way. I talk about them as Rosetta Stones in the sky. They're the things that by studying them, and you say, why? Why would we study these things? Well, in studying these things, we're beginning to get a deep picture of what our reality actually is. And that's a remarkable idea, but it's a beautiful idea that runs through all of science.
What is a black hole and how do we find them?
So a black hole, it's interesting that the idea, or the first glimpse of them theoretically, came very shortly after Einstein's theory of gravity was published in 1915. Although it wasn't recognized as such at the time, this glimpse. Essentially, what does Einstein's theory do? It's important for what follows. It's a theory of space and time, and how space-time, which is often described as the fabric of the universe, responds, warps or curves, to matter and energy in the universe. So the equations, basically the theory that Einstein published all those years ago, will say, give me some distribution of matter, something like a ball of matter, and the equations will tell you how the fabric of the universe is distorted. And by the way, the force of gravity in that theory then is the response of everything else in the universe to that distortion. So Einstein would say, what are we feeling now? Newton would say it's a force between us and the Earth, right? But Einstein would say there isn't a force. What we're responding to the distortion in the fabric of the universe created by the Earth. So that's John Wheeler, actually, the great physicist, put it beautifully. He said, matter tells space-time how to curve, and space-time tells matter how to move. And that's it. Right?
That edge beyond which there's no return, we call the event horizon. It's a horizon. The universe has a horizon too. It is a distance beyond which no information can reach us because the universe isn't old enough for light from anything beyond that horizon to have gotten here yet.
Stephen Hawking, back in the 70s, published a paper. The initial one was called Black Hole Explosions, which is a great title for a paper. Yeah. He calculated, he found out that black holes, in his language, he said black holes ain't so black. Like, they glow in the sky, like coals in the sky, and they radiate. And so over time, they lose energy and mass and ultimately disappear over huge timescales. And that's so important. And I show this picture in the show, that if you go into Westminster Abbey and look on the floor of Westminster Abbey, on Stephen's memorial stone, then you find his equation for the temperature of a black hole literally chiseled in stone on the floor of an abbey. So you might say, why? Why is it so important? This was the key. This was this Rosetta Stone idea in trying to understand what happens. What happens to the stuff that fell in? It was when you thought these things existed forever, which is pre-Hawking, right? Then you think, well, it's okay, it gets locked up inside, it can never get out, we don't care. But the thing evaporates away, one day it will be gone. So then suddenly you have to be faced with this question, what happened to everything then?
The more mass is in a black hole, the bigger the black hole becomes. In fact, if you run the math on it, it's linear. So a black hole that's twice as massive as another one will be twice the diameter. 10 times as massive. The event horizon, which is our practical definition of the size of the black hole, will be 10 times as long.
If I throw a book into a black hole, is it somehow possible in the far future, if you collect all this so-called Hawking radiation that comes off, is it possible to reconstruct the information in the book? And that's been a question, simple question, that's driven this tremendous amount of research for 50 years. And it was pretty much solved in 2019, actually, and 2020. Pretty much. I mean, there's still a huge number of questions. But roughly, the statement is everything comes out again. All the information comes out. So everything that fell in principle, in the far future, you could reconstruct the information of everything that fell in. It's an astonishing idea. Because the last thing I'll say is that before the Hawking papers and before this modern understanding, inside a black hole, just according to Einstein, sits the end of time, which is an astonishing thing to say, because we can see them. We have a photograph of one of these things in the center of a galaxy, two actually now. And when you look at that photograph, you're looking at the end of time in space. So then you think, well, if things go to the end of time, how does everything get out again?
Yeah.
And that's the content of this tremendous work in theoretical physics.
Given the mass of the universe, how big would the black hole be that contained this much mass? It's the size of our universe to our horizon. And it's like, wait a minute, could we be one giant black hole? The average density of matter contained within the size of our cosmic horizon matches right on with what you'd get for a black hole this size. That's intriguing. Maybe it's just a coincidence. What would it mean anyway for us to be inside a black hole? How would that work? Well, it turns out if you run the mathematics of Einstein's general theory of relativity into a black hole, it turns out a whole new space-time opens up on the other side. And you look behind you and the entire future history of the universe unfolds relative to your time frame. And so the universe you came from basically ends and a whole new universe opens up in front of you. Are we that universe that opened up in front of us? Okay, these are mind-bending questions.
The black hole, the idea behind the black hole is, let's say you take the sun, a star the mass of the sun, and you just collapse it, and you keep on collapsing it. You get to a point when the radius of the sun is not 700,000 kilometers, which is what it is in miles, 500,000 miles. I'm going to use kilometers because I can't remember the things in miles.
Our audience will appreciate that.
Everyone can convert it afterwards, right? So 700,000 kilometers. And you squash it down, and you squash it until its radius becomes 3 kilometers. Then there are several ways to look at this. One is that on the surface, the speed you'd have to travel to escape its gravitational pull, it's called the escape velocity, would exceed the speed of light. That's one way to think about it. So even light rays emitted from the surface, if you could squash it down that far, would just stay there. They would not escape because they'd be trying to go at the speed of light, and the escape velocity is the speed of light, and they just stop. What happens then, if a star collapses inside that number, which for the mass of the sun, 3 kilometers, is called the Schwarzschild radius, then it will collapse without limit. Nothing will stop it. And so all you will get is essentially the geometry of space and time, the curvature. And that's a black hole. So it's a thing that traps light in that sense. So you think about that. If you have this surface, and space and time are so distorted there, that if you go in across that surface, it's called the event horizon of the black hole, then you can't get out.
And our black hole is less massive than the one in the center of the Andromeda galaxy, our nearest big galaxy.
Do we have black hole envy?
Well, I think we do. Yeah, some black hole. So, but we're talking about hundreds of millions of times the mass of the sun. But it's a black hole, so it's small for that much mass.
Wow.
And so that's why. Oh, so we do it for our galaxy, then we do it for a neighboring galaxy. Wait a minute.
Go ahead.
And we can't, no, other galaxies are far away, so ground-based telescopes, you can't see it, so we send up Hubble. Mm-hmm. And so we say, well, if we have it, and we're not really a special galaxy in the universe, and Andromeda has it, our nearest neighbor, maybe, this is astronomy think. These two galaxies have it, maybe every galaxy has it.
Right.
Okay? Because why should we be special?
Right.
It's called the Copernican principle. You're probably not special.
Right. Exactly. Copernicus, better known as my father. You're not so special. I don't know what you think. But
This work, studying black holes, which is probably, it's one of those things that a certain kind of person says is useless, right? You say, why? Who cares, right? It turns out that the techniques that are being developed and the understanding that's being gained from looking at these things has got a very strong crossover with building quantum computers, right? Which is the quantum computers are in laboratories now. They have a tremendous potential to revolutionize our civilization. Incredibly powerful computing devices.